All right, the last piece of impact that we want to consider is case 2 of oblique impact, and that's the case where two traveling particles collide. All right, looks like the dog licked my paper for some reason. She stepped on it and then licked it. I don't know what this smudge is. Looked like he was eating something nasty there, but whatever. So let's look at our little drawing here. We have two particles here, or two discs or balls approaching each other, and they're going to contact right there at this point right here. So what we find is we have to do the line first, or discover the line first. The line of impact is the line connecting the two mass centers, so I'll put the mass centers there and draw the line through that, and then the plane is going to be perpendicular to that. We'll note that as they approach each other, they have components in both the line and the plane. So whatever the angle is, it could be with respect to the line or with respect to the plane, doesn't really matter. But there's going to be a component in this direction, which will be the component of this velocity in the plane, and another component in the line. The same with this guy. He'll have a component in the plane and a component in the line. So you have to do some trig to try to figure that out. After they collide, as they exit, they're going to exit at some other angles, and they'll also have components in the plane and the line, and plane and the line. All right, so that's going to be most of the work, is just doing the trigonometry. But the rules that we need to remember are: along the plane, the approaching velocity is the same as the exit velocity, or the exit velocity is the same as the approaching velocity for both particles, or for each particle, however you want to say it. For either of the particles, the exit speed on the plane is going to be the same as the approaching speed on the plane. Okay? Then on the line, we have to do a little more work. We have to do a momentum equation and the coefficient of restitution equation. All right, we've done a little bit of that already, so let's proceed with the problem. Here's a problem I kind of drew for you a little bit before, but I have a little bigger picture of it here, and we're going to say that these two particles are coming in these two directions. These are the approaching speeds and angles that they're coming in at, and they're going to collide along this line of impact. Again, the mass centers are right here, so I can draw the line of impact as the line connecting those two mass centers, and obviously the plane of impact is going to be perpendicular to that. All right, we can see that this guy here weighs or has a mass of 6 kilograms. This one here has a mass of 4 kilograms, and they are approaching each other on this speed, or this angle of 30 degrees relative to some reference line. I guess this could be the x-axis or something like that. But anyway, I don't know if you can see that in the video, but that's a 30-degree angle here that the line of impact makes with the reference angle, or the reference line. All right, so what we'll need to note, or what's obvious to note, is that if I draw this line out here, if that's a 30-degree angle, then this is obviously a 30-degree angle, so that the angle that the approaching velocity makes to the line of impact is actually a 75-degree angle. Same thing that can be done over here, that this is actually another 30-degree angle, so the approaching velocity that this guy makes with the line of impact is 60 degrees. All right, so that little bit of understanding is helpful to try to figure out the approaching velocity as with respect to, or measured from, either the line or the plane. And this one, it's easiest to do it, I believe, with respect to the line. All right, with that, then let's do this. Sometimes it's easiest to orient the picture with the line and the plane in the horizontal and vertical situation, so it's just easier to see. I don't know, it's really up to you whether that's helpful for you, but sometimes it's helpful for me. So I've just redrawn the picture here with the line and the plane being kind of in the X and Y orientation. Maybe it's a little bit easier to see. All right, so we previously defined that 75-degree angle and that 60-degree angle. We have some approaching speeds of each one. We have a mass of each one. We know that there's a component in the plane. This is the plane now. Component in the plane. We know that this component for particle A is going to be the same as the exit component. This component for particle B on the plane is going to be the same as that guy. So that's nice. It's easiest to work with the plane first. So let's say that we have for particle A, we know that the approaching speed v VA1 in the plane is going to be equal to VA2 in the plane, and that's equal to 10 times the sine of 75, and that's 9.659. Again, we need to make sure we keep our positive and negative straight, so let's define that as our positive and this is our positive, so x's and y's or something like that, so because the signs are going to be especially important. For particle B, along the plane again, it's going to have a negative, if I define that as positive, and then this is going to have a negative speed and it will continue with a negative speed. So V plane 2 for particle B is equal to V plane 1 for particle B, and that is negative 5 sine of 60, which is equal to minus 4.3. All right, so we've done half the work actually, finding the two exit speeds for the two particles. Along the line, it's a little more algebra, but we notice that the beginning velocity or beginning momentums have to be equal to the ending momentums. So the momentums along the line, this is the line, so I'll have a positive 6 kilograms times the velocity in this direction, which will be 75 cosine 75. Or excuse me, 10 cosine 75. So this is 6 kilograms, and the velocity is 10 cosine 75. This one is 4 kilograms, and the velocity in the line is going this way, so that would be 5 cosine 60. And so we see that. That's going to be equal to the mass times velocity plus the mass times velocity of the exit. Now those are the two unknowns we don't know. So I can simplify that a little bit, and I can find that I have one equation with two unknowns. Let's find out from our restitution equation. Again, we don't know our exit speeds, but we do know our approaching speeds, and those are given as just before. The approaching speed is, for A, was 10 cosine 75. We need to subtract the approaching speed of B, and that is negative, but the approaching speed was also a negative, and so this is where most people kind of get mixed up, is putting the double negative, where it's required anyway, in the denominator. So if you have a negative times a negative, obviously you have to take that into account in your algebra. All right, when we do that, we can set up this equation as another equation with two unknowns, and we just do just a little bit of algebra, and we can solve this two equations, two unknowns situation, and find out that VA line 2 or the velocity in the line direction for particle A is negative 6.6683. The velocity in the line direction for particle B is positive 2.385. In order to find out the speeds, we just take the square root of the sum of the squares, and we get 9.682 for particle A, and for particle B we get 4.94. So again, the process is not very difficult, it's just following the rules. It is very much a plug and chug, algorithmic kind of approach to finding the exit speeds.